the continued fraction algorithm. So what we have is we have z over 2 to the 2l is approximately d over r. And we want d over r. And we also know r is much smaller than 2 to the 2l. So first, let's think about this in terms of information. How much information is there? How much information in Z? Well, the answer is 2L bits. How much in dr? Log d plus log r bits, roughly. So what we need is we need r to be, or we need 2 to the 2l to be roughly r squared. And in fact, we're going to show it works as long as 2 to the 2l is bigger than 4r squared. So so this 2l for an n-bit long number, for a l-bit long number, if we want to factor an l-bit long number, we need 2l registers for the function and another l registers for the result of the function. Okay. So continued fraction is an algorithm which finds all good approximations to a real number. Finds all good approximations. Where there's a technical definition of good approximation we won't use. And what is it? Well, let's say r equals 15, and we get 887 over 1024. So this was the output of our quantum computer, and this was 2L, where we're using 2L bit register for the quantum Fourier transform. So this is equal to 0.86621. The first thing we do is we take this number and we write it in continued fraction form equals 1 over 1 plus 1 over 6 plus 1 over 2 plus 1 over 9 plus 1 over 3 plus 1 half. So 887 equals that. And the continued fraction is, well, 16292. So just these pieces of the numerator of the continued, pieces of the denominator of the continued fraction. So how do we do this? It's actually pretty easy. And I'll just do it by example. 0.86621 equals 1 over 1 plus 0.154454. So we divide 1 by this number, and we get 1 plus a remainder. So 1 over this is 1 plus 0.1546. Well, this is equal to, well, we're going to do the same thing. We take 1 and divide it by this number, and we get 6. 1 plus 1 over 6 plus 0.4744. And you can guess what we're going to do next time. We're going to take 1 and divide it by this. And that's equal to 1 over 1 plus 1 over 6 plus 1 over 2 plus 0.1079, etc. And we keep on doing this. Well, either until, well, in this case, we can keep on doing this until we reach the actual rational number 887 over 1024. Yeah?
Will these, as you progress through the continued fraction chain, will these always be underestimates?
No, they're going to alternate being
Under and over?
and I will, well, actually, all of these things are exact. This is equal to this, is equal to this, is equal to that, because I've added this thing. But as you can guess, the convergents are, first convergent is 1. Second is 1 over 1 plus 1 over 6. That equals 0.8571. That's under. The next is 1 over 1 plus 1 over 6 plus 1/2. That equals 13 over 15. And that's 0.86667. And the next one is 1 plus 1 over 1 plus 1 over 6 plus 1 over 2 plus 1 over 9. So we're just taking the first few things of that. That is equal to 123 over 142 equals 0.866197. And I'm not going to go through any more of them. But you can see that this first one is over, the second was under, third is an overestimate, but it's getting much closer. The fourth is an underestimate, and it's really, really close. So those are the convergents of the continued fraction. And as I say, the continued fraction is guaranteed to find all good approximations where there's a technical term for what a good approximation is, and it's not quite what you might think it is. And if you choose n, or if you choose 2 to the 2L roughly bigger than the maximum possible period squared, the right answer is guaranteed to be a good approximation. But I'm not going to prove either of these because proving it finds all continued good approximations is a little bit tricky, and proving that it actually is a good approximation in this technical term is also a little bit tricky. Although maybe I should write down what a good approximation is. Q over R is a good approximation to X. Oh, let's make it D over R is a good approximation to X if dx minus R is less than Cx minus Q for all integers for all CQ less than R. So, well, actually, Well, for all C and for all Q less than R. So if Q is less than R, you cannot get as good approximation for dx minus R. So this is what it means to be a good approximation for the continued action to find